Hello, my rubber hearts. Welcome back to the second season of My Rubber Heart and another exciting episode where we dive deep into the fascinating world of rubber. Today's episode is all about how we can improve the performance of natural rubber, or NR, through chemical modification. We're going to explore how chemists can tweak the molecular structure of natural rubber to make it even more versatile and effective for different industries. Before we dive into the science, let's quickly recap the origins and properties of natural rubber. NR, sourced primarily from the Hevea brasiliensis tree, has been a crucial material in manufacturing for over a century. It is renowned for its excellent elasticity and tensile strength and low heat buildup, making it ideal for uses like tire production. However, NR has also some limitations, such as low resistance to heat, oil, and abrasion, which can affect its performance in more demanding applications. Now, to overcome these limitations, scientists have developed methods to chemically modify NR, enhancing its properties to make it more durable and versatile. So, what exactly is chemical modification? In simple terms, it's the process of altering the chemical structure of NR at the molecular level to improve its performance. The most common target for modification is a carbon-carbon double bond presented in NR. By reacting with this bond, chemists can change the properties of the material. This modification helps NR achieve better heat resistance, oil resistance, and even flame resistance, which opens up a wide range of applications for industries like automotive, construction, and electronics. Let's look at the different types of chemical modifications, their effects on NR, and how these changes are used commercially. There are several ways to chemically modify NR. These methods can generally be categorized into three main types. The first one would be changing the molecular structure or lowering the molecular weight of NR without introducing new atoms or molecules. The second one would be introducing new atoms or molecules at the carbon-carbon double bond, altering its chemical and physical characteristics. And the third one would be grafting other molecules, which are short or long polymer chains, onto the NR backbone. Each of these techniques leads to changes in physical and mechanical properties of NR, making it suitable for different applications. One of the ways to improve the performance of natural rubber is by altering its molecular structure or reducing its molecular weight without introducing new atoms or molecules. This method is a bit different from the chemical modifications where new atoms are added, but is just as effective in tailoring the rubber's properties. When we talk about lowering the molecular weight of NR, we are referring to breaking down the long chains of polyisoprene into shorter segments. This process can be achieved through techniques like thermal degradation or mechanical shear, which essentially break the polymer chains into smaller pieces. But how does it work? In its natural form, NR is made up of long chains of polyisoprene molecules. While these long chains give NR its incredible elasticity, they also make it more prone to tackiness and flow under pressure. By cutting these chains down to size without adding anything new, scientists can make the rubber less sticky and more resistant to deformation over time. This is particularly useful for applications where durability and stability are key, like in industrial rubber components or non-slip materials. Reducing the molecular weight of NR leads to lower tackiness, which is important in applications where the material must not stick to surfaces unnecessarily, such as in tires or conveyor belts. Improve processability, because shorter polymer chains are easier to work with, allowing the rubber to be molded or extruded more easily during manufacturing. And last but not least, reduce viscosity, which makes the rubber easier to handle in processes like injection molding or extrusion. Another method is the cyclization reaction. This is one of the oldest methods of modifying NR. This process involves transforming the linear structure of NR into a cyclic form, which makes the rubber more rigid and resistant to heat. Cyclized rubber is highly valued in the coatings and adhesives industries due to its brittle and resinous nature. Commercially, cyclized NR is used in products where increased stiffness and rigidity are necessary, such as industrial coatings and electrical insulation. Another important modification technique is halogenation, which involves the addition of halogen atoms such as chlorine or bromine to the NR structure. Halogenation significantly improves oil resistance and flame retardancy. Chlorinated rubber has been commercially successful due to its application in waterproof coatings and protective paints. Industries such as construction, marine, and automotive use halogenated NR for its superior corrosion resistance and durability in harsh environments. One of the most versatile modifications of NR is epoxidation, where oxygen atoms are introduced into the polymer chain. Epoxidized NR or ENR is commercially produced by in situ epoxidation using formic acid and hydrogen peroxide. This method enhances NR's resistance to oils and gas permeability, making it comparable to synthetic rubbers like nitrile rubber and butyl rubber. ENR is widely used in the automotive industry, particularly in the manufacture of seals, gaskets, and hoses, where resistance to oils and gases is essential. It's also favored in tire manufacturing, where it helps reduce rolling resistance, improving fuel efficiency. Hydrogenation of NR involves the addition of hydrogen atoms to the carbon-carbon double bonds, converting them into single bonds. This process reduces the unsaturation of NR, enhancing its thermostability and making it more resistant to oxidative degradation. Hydrogenated NR is particularly valuable in applications where high heat resistance is required, such as automotive parts like belts and hoses, as well as in industrial machinery components. This modification also reduces the tendency for the rubber to crystallize at low temperatures, which is a significant advantage in cold weather applications. On the other hand, in graph copolymerization, chemists attach other polymer chains onto the NR backbone. This is usually done with vinyl monomers, creating new NBR-based polymers with unique properties. The goal here is to combine the elasticity of NR with the rigidity or toughness of the grafted polymer. For example, grafting methyl methacrylate or MMA onto NR produces a thermoplastic elastomer, a material that behaves like both rubber and plastic. This hybrid material is used in various industries, including automotive and packaging, where flexibility, durability, and ease of processing are all required. Not all chemical modifications are commercially viable, though, but several have proven to be both technically feasible and cost-effective. For instance, reducing the molecular weight of NR is widely used in industry because it's a cost-effective way to enhance certain properties of rubber without the need of additional chemicals. Chlorinated and epoxidized NR are commercially produced and used in various industrial applications. Graph copolymers, although more complex to produce, are gaining popularity in specialized industries due to their tailored properties. On the other hand, certain modifications, such as hydrogenation, are more expensive, limiting their widespread use in applications where high performance justifies the cost. The chemical modification of NR has opened up its use in a range of industries, and the ability to tweak the properties of NR make it highly versatile for both traditional and cutting-edge applications. So, as you can see, the potential of natural rubber goes way beyond what it can do in its raw form. Through various chemical modifications, we can make it more resistant to heat, oils, and wear, opening the door to an incredible range of applications. From cars to buildings to electronics, modified natural rubber is all around us. That's all for today, my rubber hearts. If you enjoyed this episode, don't forget to hit that like button and subscribe to the channel for more fascinating deep dives into the world of rubber. Let me know in the comments what you'd like to learn about next. Stay bouncy and see you in the next episode.